Hello, welcome back. So today is lecture 10 and we shall conclude about our discussion on Varactors and Schottky multipliers. Okay. In the last lecture, if you recall, we introduced why Varactors or Schottky multipliers are useful and what are the different applications such as frequency mixing, conversion, harmonic generation, etc. The basic principle of a nonlinear reactance and how it can generate harmonics, and how a nonlinear reactance can be obtained from a capacitance whose value changes with applied bias, and that helps you in tuning the frequency. All these things we covered in some detail, and we will conclude that today. We will continue on where we had left last time, and we will basically try to understand a little bit more details in terms of the device limitations, about heterojunction barrier diodes, about hyper abrupt junctions in varactors, etc. Okay, we will discuss all of those in today's lecture. So over to PPT here. So this was the last slide that we had discussed in lecture 9. Okay. And if you remember, we said that elastance S is the inverse of capacitance. So if the capacitance goes from a maximum, then the elastance goes from a minimum here, and if the capacitance goes to a minimum here, the elastance goes to a maximum here, and this is the point where the device will break down. This is the point where the diode will turn on. Okay. So the maximum swing of the voltage, which also determines the maximum swing on the elastance, and that is very important, this because this gives you the range of tunability. If you want to increase the range of tunability, you have to increase this swing, that is limited by this maximum elastance by the minimum elastance. Okay. And there is a figure of merit called the dynamic cutoff frequency, which is basically the maximum elastance minus the minimum elastance divided by 2 pi Rs. Rs is basically the series resistance. If you remember, the series resistance is the total resistance of the quasi neutral region, the package parasitics, the extra resistances, etc., etc. Okay, the total series resistance is something you want to minimize, and this swing of the elastance range is something you want to maximize, so that your dynamic cutoff frequency can be maximized. Now this maximum elastance swing or this maximum voltage swing in a way is limited by the factor that it will break down here. Okay. So breakdown happens when there is a punch through, for instance. Okay. A diode can punch through. There is also something about electron saturation velocity, and the effect of the electron saturation velocity I will come in a few slides from now. And then the other limit is of course the forward turn on. If the diode turns on, it then is no longer a capacitor, it is a conductor, and you cannot use it for a varactor anymore. So punch through, electron velocity saturation, forward turn on are the three important factors that limit your cutoff frequency, the maximum swing. Okay. Now what happens is that in general we call pumping the varactor is basically when you are bringing a signal at a certain frequency fp. Okay. You are bringing the signal at a certain frequency fp, and we call it as a pumping the varactor. When you do a pumping the varactor, the elastance basically changes with time. Okay. And as I told you, you will generate multiple harmonics, you can generate many frequencies, you can generate 2fp, 3fp, etc., but you need to terminate those frequencies which are idler, which you do not want. Okay, and that matters a lot. This image, by the way, is of a symmetric varactor. A symmetric varactor can be realized using a heterojunction barrier diode. For instance, a heterojunction barrier diode will give you a symmetric CV. I will come to that when you discuss about that, and so elastance also looks similar. Okay. Now the next thing to understand here is that a varactor, as I told you, we call it a frequency multiplier when you are using it as a higher harmonic generator or a device to multiply the frequencies. We generally call it frequency multiplier, but a varactor has also other application. First of all, it can be used as a converter and a mixer. What do you mean by converter and a mixer? You can mix two frequencies, you can convert to one frequency to another frequency, it need not be a harmonic. What do I mean? You have a pump frequency of fp, that is the signal at which you are pumping the varactor, you are bringing the signal. You are also introducing a smaller signal of a smaller magnitude amplitude at a frequency of fs. This is your signal frequency, this is your pump frequency. Because the two frequencies are coming in, okay, and it is at a varactor such as this could be a 2 terminal device. So you are basically feeding into the same port essentially. Okay. So what happens is that you are bringing in two frequencies, they will mix. So you can get frequencies in the form of this n fp plus fs, where n can be negative. Now you will get an output frequency. If the output frequency is larger than the input frequency, and in this case the input frequency is this, then we call it up converter. and if the output frequency is less than the input frequency, we call it a down converter, right. We call it a down converter. It need not be always up converter, it could be down converter also. And even in down converter and up converter, depending on n equal to -1 or 1, you can call it upper sideband, lower sideband, etc., etc. And because you are pumping it at a certain frequency and you are bringing in another frequency on top of that, there could be stability issues. You know what is stability issue? You can have like an infinite gain, okay, like a feedback, it is infinite gain, and you can have unwanted oscillation. It can be unstable, okay. It can be unstable, and it is also quantified by a negative resistance at the input or output, and we do not want it to be an unstable element, okay. But in general, Varactor is a good frequency converter, you know, because it has good noise properties and gain. If you can minimize the series resistance, your noise will be lower, because series resistance is the source of noise. It can also give you gain, by the way, okay. Frequency converters can also give you gain, and that gain can make it as a parametric amplifier actually. Okay, so we are coming to that next. A parametric amplifier is basically you are going to amplify an input signal, although this is not the best kind of amplifier. It is a 2-terminal device, it could be a 2-terminal device, and then a 2-terminal device is not a good way to amplify, because in an RF or a microwave system you always talk about port, not terminal. For instance, this is signal and this is ground, so this is a port. If you have a 2-terminal device, this is a 2-terminal device, it has only one port. So the signal is coming in here, the signal is also output also coming out here. So the same port you are feeding in the signal, you are getting the signal out, because there is only 2 terminal, one is a signal, one is a ground. So 2 terminals form one port. So in the same port you are basically putting in the signal, you are putting in the signal out, and that is not a good thing, because you will get a lot of unwanted reflections, and this is not the best way to amplify. But still, parametric amplification is an important and an interesting concept. What it means is that you have a signal at say frequency fp, and it is a very strong signal, it is a very strongly pumped signal, and you have a small signal at another signal frequency fs, just like mixing, just like frequency conversion and mixing. Now if you terminate the idler frequencies and all other frequencies in an appropriate manner, then you can actually expect the varactor to have a negative resistance at the signal frequency. At the signal frequency you are talking about a negative resistance. Why? Well, because when you have this, when you bring in 2 different signals, you are actually mixing them up to get say fp minus fs, okay. That is your mixing product you are getting because of the nonlinear reactance. Now if you also bring a current at this signal, okay, if this is an idler frequency for instance, and this is not useful, but if you are bringing a current at this signal, this will also mix with fp and fs, correct, and it will further mix and it will create more harmonics, and it will eventually generate power at the signal frequency fs, okay. What is happening is that you have 2 signal fp and fs, one is the pump frequency, one is the signal frequency, they are mixing up and producing power at a certain frequency fp minus fs. If you also bring in another signal now at fp minus fs, or you let current flow at this frequency, then it will also further mix with fs and fp and create further harmonics, okay, and it will generate power at fs. If the generated power at fs is more than the power that you are supplying at fs, total power is conserved, because you have multiple harmonics and all the things, so your total power is conserved. But at signal frequency fs, if your output power happens to be, or the power generated by this mixing happens to be more than the power that you are bringing in at that signal, then you are saying that there is a gain, and you can correlate with a negative resistance. You can say that the device has a negative resistance, you can say that there is a gain in this varactor, we call it a parametric amplifier at that case, in that case, okay. In that case we call it as a parametric amplifier, alright. So this is an important application, and although not very as widely used as a frequency conversion or a tuning, but it is still very useful. And of course we have already talked about voltage tuning, but we will discuss a little bit more. I told you, just because a variable capacitor or a varactor you can tune the capacitance using voltage does not mean it is the only element in a voltage tuner or in an oscillator. For instance, this voltage tuning could be one component in oscillator. So if you have a VCO, VCO stands for a voltage control oscillator, and I told you in the first slide of lecture 9 that a voltage control oscillator is very useful in a receiver circuit. For instance, you want to generate a local you want to generate a local oscillating frequency to mix with an incoming RF signal. So, you can use the varactor as a component in a VCO circuit. You can actually use it as a part of that resonance circuit which you are going to tune, because with an applied voltage you are going to change the capacitance, you are going to change the frequency of oscillation. And so, if you change the frequency of oscillation, so essentially you can change the frequency from F min to F max as you are changing the elastance to S min to S max or your capacitance. Okay. So, what happens is that if this is your capacitance and this is your voltage, this is the capacitance, this is your C max, okay, and this is your C min, for instance, the minimum capacitance. Beyond that the breakdown happens. So, C 1 by LC, this is your omega, the resonant frequency. If your C is high, then your omega is low. So, the maximum capacitance corresponds to basically the minimum frequency, and maximum capacitance of course means minimum elastance. So, essentially minimum elastance corresponds to the minimum frequency. So, if you go from the minimum elastance to the maximum elastance in that swing, you actually go from minimum frequency to the maximum frequency. This is the range of frequency you are tuning, and so the tunability is typically expressed by this ratio, the maximum by the minimum frequency of tuning is given by the square root of the maximum elastance by minimum elastance. Okay. Since the elastance is nonlinear, what I mean is that if you go back to the previous slide and you see, yeah, this is an elastance, it is a nonlinear elastance. Okay. It is very steep here and it is flattened here. So, it is a nonlinear. So, what we can see is that your tuning range is actually not linear, because your elastance is not linear. It is steep at low voltage, it almost saturated high voltage. So, that kind of factor also comes into picture. You do not expect a linear tuning range. Okay. The next thing is that even in a Schottky diode or a PN diode, we typically talk of an abrupt junction, where say in a PN diode you have a P and then you have an N, which is an abrupt junction. But by changing the doping profile, in a Schottky diode or in a PN diode, does not matter, you can actually get you can get a CB profile which changes in a different way. It is nonlinear, but the rate of change of capacitance can be more sharp. What I mean is that if you look, this is the basic Poisson equation of the depletion region. We have discussed this in the basic semiconductor device courses. If the dopant N is constant, okay, that is an abrupt junction. If the dopant changes as a function of X, which is the depth, if the doping is changing as a function of the depth, then we can say some kind of constant into x to the power m. If m equal to 0, then it becomes B, which is an abrupt junction, which is what we typically discuss. If m equal to 1, then it becomes Bx. It is a linearly graded junction, which means the doping is linearly changing, correct. If m equal to 2, then it becomes Bx square, right. Now, m can be also less than 1, say m equal to minus 2. So, it will be B x minus 2, or it will be n equal to B by x square. Those are called hyper abrupt junction. So, this figure is the first figure is showing you the doping as a function of x. So, if it is an abrupt junction, then the doping is constant, is 0. In a Schottky diode, for instance, the doping is constant. If you have x equal to 1, that is a linearly varying one, the doping is linearly changing. X equal to 2, it is a parabolically changing function. Oh, sorry, this is the x equal to 2. X equal to 3, it is a cubic function, the doping is changing. Now, if x equal to minus 1, minus 2, etc., then you are looking at this, or you can see here they are using m equal to minus 5 by 3, minus 3 by 2, etc., some kind of different numbers they are using, and they are getting these different profiles here. You see the doping is changing like that, right. So, if you use a generic expression like that, you can actually write the depletion capacitance as something like that, as a function of m, and you can simplify that as 1 by the square root, the s at set square root, okay, it is to the power minus 1 by s of Vr plus the built in voltage. So, s is equal to 1 by m plus 2. Okay. So, for instance, in abrupt junction m equal to 0, so s equal to half. In a linearly graded junction m equal to 1, so s will be equal to 1 by 3, which is this linear. Abrupt is this linear. Here I am plotting the log of the capacitance with respect to log of the reverse voltage. So, although the actual capacitance changes non-linearly like this, but in log plot it looks like a linear plot, of course it is a log plot. Abrupt also looks like that, graded also looks like that. However, if your m is equal to say minus 1 by 3 or minus 5 by 3 etc., your S will be for instance 3, and in that case your capacitance changes so fast in a log scale. In a log scale your capacitance is changing so fast. So, imagine in a linear scale how fast it will change. So, this is called a hyper abrupt junction, where by tailoring or tweaking the doping profile you are able to get a capacitance profile such that the capacitance value changes much more abruptly or much more it is much more sensitive to the change in the voltage. Higher this S, higher this quantity S, more is the sensitivity of the capacitance with respect to voltage, or in other words the variation of the capacitance with applied bias is higher. So, hyper abrupt junctions are useful for more sensitive varactors. You can have very sensitive varactors using hyper abrupt junction, but in a normal chip it is not so common to find this kind of hyper abrupt varactor diodes, because the fabrication cost is more. You have to do a special ion implantation or an epitaxial doping, and it involves more cost on a commercial scale. For academic research is better, but even then this is very useful in a context that you can actually have the freedom to choose a varactor with a more abrupt or more sensitive variation at voltage. So, that is called a hyper abrupt junction. Okay, you can, this is about how sensitive in what sensitivity can you tune the voltage in, and hyper abrupt junction is much better than a linear junction. Now, there is a device limitation in all of this, by the way. Whenever you have a Schottky diode, suppose you have a Schottky diode, you are putting a Schottky contact here and you are putting an ohmic contact here, correct. You are having a depletion region. The more negative voltage you apply, say minus 2 volt, you are going to minus 3 volt, the more it will deplete. Whenever it depletes, that amount of charge delta Q has to flush out through this ground terminal. So, that charge that is flushing out in a very transient time is called displacement current. The displacement current flows through the capacitor because it is a very transient process. Very quickly when you are changing the bias, the extra charge is flushed out or flushed in through the ground terminal, and so that is a displacement current that happens in the capacitor. But the displacement current also has to flow through the neutral region. This is the neutral region, or this is the resistive region. The series resistance is there, no. So, the displacement current has to not only flow through the capacitance, but also has to flow through the undepleted resistive region whenever the voltage is changed to tune the capacitance, because that extra delta Q or delta plus minus Q is being flushed in and out in a displacement current. The displacement current has to flow through the resistive region also. So, this is the equation. Essentially what is happening is that if I write the charge as basically your the charge is basically your C into CV. So, it is CV and V of t. So, the voltage is varying as a time, capacitance is changing as a voltage, and voltage is varying as a time. Okay. So, this Q of t is basically nothing but IT into dt. So, that is what this equation means. Okay. And if I say that the voltage is now in the form of a cos omega t, that is my sine wave, then if I do this derivative, then I get this expression. This is the displacement current. This is the displacement current that also flows through the undepleted resistive region. Please remember that. Okay. You can see that if the frequency is high, omega is high, or if the RF voltage is high, then this quantity also will be high. Now, this is a problem. At lower or modest current levels, the resistive region can support that, because the resistive region, there is some voltage drop in the resistive region, the neutral region, and as you are increasing the voltage or as you are increasing the frequency, you are getting more current. The resistive region can support that current, but at one point saturation velocity kicks in, and the maximum of electron at high field, at maximum current that can flow is the product of charge, which is doping times the Q into the velocity. If the velocity has reached saturation velocity because of the high field, then you can no longer accelerate the electrons any further, which means the current in the undepleted resistive region cannot increase beyond this quantity. This will limit the multiplier performance. Why? Because the charge at the undepleted region, the delta plus minus Q that you are flushing in or out, will take a finite time to travel to the ground or from the ground terminal, and so the time rate of change of capacitance could not be as fast as you want it to be. So, essentially you are changing the capacitance in a tuning the voltage, but the rate at which you are doing that could have a limitation, because eventually your displacement charge, the amount of displacement charge that you need to also flush out through the resistive region cannot be supported by the resistive region because velocity saturation has kicked in. Okay. So, it will do it slowly at the rate at the velocity saturation will put a limit on the multiplier performance. Okay. So, at high current levels, so at high frequencies, if you are going to really high frequencies, millimeter wave and high voltages levels for instance, then there is a device limitation that comes into picture, and that will put a limit on your multiplier performance. Of course, you can increase the doping to increase the current level, but if you increase the doping, the breakdown will become poor. So, what is the point? If your breakdown becomes poor, your elastance swing also becomes low. So, that is a trade off there. Okay. And the last thing on this topic is basically your heterojunction barrier, quantum barrier varactor. So, this actually shows you the conduction energy profile. So, you have a lower band gap material which is n-type dope, then you have a wider band gap material which is undoped, then again you have a lower band gap material which is n-type dope, and you have an ohmic contact here. So, this part is for instance and this part for instance lightly doped, it can be depleted. Okay. And what is happening is that your capacitance will look symmetric like that. So, your elastance S of t goes something like that, correct. It is a because when you apply a positive voltage on this side or negative voltage on this side, or you apply a negative voltage on this side or a positive voltage on this side, does not matter, it is a symmetric diode. One side of the depletion will shrink and the other side of the depletion will expand. So, there are two depletion regions in series, two depletion capacitances in series, this is C1, this is C2. So, no matter what you do, your capacitance will decrease. So, the maximum capacitance occurs at 0 voltage, either at +1 +2 or at -1 -2, your capacitance will decrease, because as I told you there are two capacitances in parallel in series, one is going to expand, the other is going to shrink, one is going to shrink, the other is going to expand, does not matter whether you are applying negative voltage or positive voltage on either side. That is why the capacitance is maximum at 0 voltage, and this is called a quantum barrier varactor or a heterojunction barrier varactor. And you can see that this is what I mean, one side it will expand, the other side it will be low, or vice versa. And the way to fabricate this is that you have to grow different layers. So, you have this stack which is repeated say many times, 5 times or 10 times. So, there is a lightly doped 300 nanometer say gallium arsenide, there is an undoped 5 nanometer could be gallium arsenide or aluminum gallium arsenide, and then you have a barrier of say 10 nanometer which is highly wide bandgap material like indium aluminum arsenide or L-gas, which is a higher bandgap material, and then you repeat this stack for many like a stack, okay, or you may not repeat, it depends, and then you have again you have an n-type dope layer under contact. So, you form ohmic contacts on both sides and you make this symmetric diode, and if you do the math, apparently it so happens that this kind of a symmetric varactor diode only produces odd harmonics, which is very good. In many application you only need 3 omega or 5 omega, and this can do the fit the bill. And because in modern day microelectronics are heavily using actually more advanced forms of varactor diodes, Schottky multipliers, you can easily get up to terahertz, more than few terahertz, more than 1 terahertz by using at millimeter wave frequencies. You can do a frequency quintupler 5 omega, and you can get up to terahertz for instance. Another thing to note in all these frequency multipliers is also the output power that you are delivering. How much power are you delivering at a certain frequency? Suppose you have a certain power at a frequency omega and you want 3 omega. How much power are you delivering there? That is an important thing, and with what efficiency are you doing that? Usually power and efficiency both cannot be simultaneously very high, which means if you want to achieve higher efficiency, it is low power. You are bringing in low power, you are getting low power, but the efficiency is high. Or if you want to higher output power, you also have to bring in higher input power, okay, and then the efficiency will be low. So, there is always this trade off that comes into picture, but this is an important concept. Okay. So, with that I think we can conclude this lecture on lecture 10 on varactor diodes and Schottky multipliers. So, we understand that these are devices where capacitance can be tuned by applying a voltage non-linearly, and by doing that you can get a tuning element with which you can actually you can use that in a resonance circuit and tune the frequency in an oscillator. You can generate frequency harmonics because of the nonlinear reactance. You can also do frequency mixing, frequency conversion, and these are widely used in mixers, frequency conversions, and also your oscillators. Those circuits are not a part of this course curriculum, but it is important that we understand in those circuits we use this kind of devices, and these devices are actually Schottky diodes or PN diodes or even FETs. So, depending on the technology you are using, depending on the chip, depending on the production line, people decide what to choose for, whether it is a gallium arsenide MOSFET, whether it is a CMOS MOSFET, or it is a bare planar Schottky diode or a PN diode. The choice depends on the designer, the cost, the time to market, so many other things. Okay. So, with that we will conclude lecture 10 and week 2. Now, week 3 we will have 4 lectures, 11, 12, 13, 14. We will talk about transfer electron devices and avalanche transit time devices, impact devices, okay, impact and gun diodes, and they are useful for generating RF signals. Okay. They are also useful for generating RF signal, and we will discuss about those devices in lectures 11 to 14. Okay. Thank you.